Hi, welcome to Unit 72. In this unit, we're going to talk about the different stars in the Milky Way, and then also how the Milky Way is interacting with its neighbor galaxies. And that's going to be actually a generalization, not just for the Milky Way, but for also other galaxies out there. So this is a typical behavior for other galaxies. So anyway, we're going to list type 1 and type 2 population basically stars in the Milky Way and how they were discovered and the differences between them. And there is actually population 3 stars that are also going to be mentioned. Explain how distinct stellar population may result from galaxy formations, basically. And describe the evidence for the merger and cannibalism, basically, between galaxies. Our galaxy is in the process of, actually wasn't, it's still an ongoing process of basically eating other galaxies in the process, okay? And then it's going to do so in about 1 billion years for the both Magellanic Clouds, the large and the small. And it's also going to merge at some point about 5 billion years from today with Andromeda, the larger galaxy in the neighborhood, okay? So Walter Bade discovered that there are two types basically of galaxies. Uh, he classified them in population 1 and population 2. Population 1 stars are really on the same plane of the galaxy and they orbit in a circular path around the galaxy and they have high metallicity. In other words, they have more, about 3% of their mass or their structure is made up of elements that are heavier than helium. Okay. Okay, so that's really what these stars are. Versus population 2 stars. Population 2 stars, they're actually, their path is all over the place. They are not on the ecliptic, they are not on the, I shouldn't call it the galactic plane, but they are everywhere, number one. Number two, their paths are more elliptical. And number two, they are poor in terms of metallicity. They don't have heavier elements than helium, as does population 1 star. So that's basically the biggest distinction between two stars. So here is a table in here. In terms of age, population 1 stars, they're a lot younger, okay? And they are actually mainly in the arms of the galaxy, okay? Versus the population 2 stars that exist in the halo of the galaxy outside, basically in the entire basically structure of the galaxy. And in terms of color, they're blue, which means energetic. They're actually usually bigger in size, whereas this one are red and old. Okay, and the orbit, this ones are more circular, regular paths. This one are all over. Okay, plunging through the disk and approximately elliptical orbits. And in terms of structure, these are high in metals, basically. Anything heavier than helium, anything heavier than hydrogen actually is considered a metal in astronomy. Okay, so we don't necessarily mean a metal like iron and nickel and all of the other metals, but actually anything that is not the elementary structure here. So in this case, it's meant with any element more than helium. And that's about 3%. Remember, the sun is mainly 3/4 hydrogen and about a quarter helium, and the difference is actually those higher metals, okay? Higher elements in the periodic table. Type 2, I mean, population 2 stars, they are actually very low in that, about 10 to the negative 2 or 10 to the negative 3 suns, basically, extremely small and like the sun, okay? Now, when they arranged them, they saw that population 1 stars are mainly in the arms, at least in this case, I'm looking at Sagittarius arm, Cygnus arm, Perseus arm. Those are some of the nearby arms where the stars O, A, and B are located. But further away arms are kind of a little bit because of the galactic cloud, it's very hard to see them. So basically that there's an ongoing work, but that's basically how population 1 stars are. Okay. So again, there is actually even poorer in terms of metallicity than population 2, and that's population 3. So those must be the stars that form immediately when the galaxy was formed. Okay. By now, most of them are either gone, except when they are small, too small. So those, they retain their structure for a long, long time. So they probably exist out there, and that's an ongoing work for them. But that's when the galaxy formed, immediately after the Big Bang, the Milky Way formed. And population 2 stars are probably from that age also, or actually coming from the remnants of other galaxies, smaller galaxies that went through their star formation quickly, and now they are in the process of being basically observed by the sun, by the Milky Way. I'm sorry. We're talking on a galactic scale now. Okay. Population 1 stars are still forming. Okay, that's basically what we're talking about in this case again. So, evidence of galactic cannibalism is out there because there are stars that don't fit the picture at all. They are not in the galaxy, and there is formed these streams in here that the only way could explain those kind of structures is through a process through which the Milky Way is gravitationally basically attracting the gases from those stars. So basically, as they go through one pass through the Milky Way, they lose most of their gas that gives them the ability to produce more stars. So it's only the older stars that seem to remain in those streams. And they're also bound to the Milky Way. So at the end, basically, they will be starved from galactic clouds to form stars, and also they will be actually absorbed by the Milky Way. So that's basically what's going on. This is actually not unique feature to the Milky Way. Big galaxies also, they become big by this process. Same thing is going on with Andromeda, and same thing with going on with the Triangulum and other nearby galaxies, and even further away galaxies. Okay, at least the ones that we can see that they have uh, satellite galaxies like the Milky Way and the other nearby galaxies that we can see, because probably that's what's going on also in the faraway galaxies that we can see that are neighbors. Okay. Again, as I mentioned before, the Milky Way right now has produces star about 10 stars per year. Okay, because it has enough material, enough gas that coalesces. As this process goes on, the matter, yeah, the big matter stars, what they do in this case, they collapse and they redistribute matter through the galaxy, and they basically allow this process to continue more or less. Whereas the smaller stars, they retain this material. So that's how the galaxy will also be basically running out of material to make new stars, because the smaller galaxies, they will keep those materials. But there is another way for the Milky Way to actually get more and more material, and that is by absorbing other galaxies. Like in this case, in about 1 billion years from today, both the small and the large Magellanic Clouds, they will be observed by those are two separate galaxies. They're about 150,000 years from 150,000 light years from the Milky Way. Okay, so they're nearby galaxies, both of them, and they're going to be observed. Whereas the Milky Way and Andromeda Galaxy, and before that the Triangulum Galaxy, they will all three merge into a big galaxy that is going to be the dominant feature in the sky. Here is the thing about it, though. This in about 5 billion years. That's a rough number, okay? Andromeda Galaxy is about 2.5 million years from here. 2.5 million light years from here, I should say. That's the distance. The structures are actually started to merge as we speak. So the interaction is ongoing, and the intergalactic cloud that is between them, or at least the stars that are between them, are being impacted. So this process is an ongoing process. It's going to take a long time to complete. This is in terms of the Milky Way. What we know about the Milky Way is most likely happening with all of the galaxies in the uh, in the um, in the universe, as long as they are nearby and they can do this kind of processes. If they are isolated, then they are isolated. Thank you.